Welcome, welcome to another extravagant, great day of Algebra 2 Extended, Lesson 9.2, Day 1. A little bit more work with exponential functions. However, people might like today's a little bit better. We'll see. I might be wrong, but at least you'll like the beginning portion of it, I think. We'll see. Today we are going to be doing Day 1 here, and you're going to watch the video, and to top it up, there's no homework today. We're going to finish this lesson up tomorrow, and then you'll do 9.2 try on your own. And then I believe Monday is going to be the review. This is a short 2-section unit. Monday will be a review. Tuesday is going to be the quote-unquote test for this 2-section chapter. So be on top of it. And all your homework and the review will be probably due Monday or by Monday. So we're going to keep going from there. What you're going to be doing in your warm-up here, I don't know if you remember ever seeing this equation before, but we're going to be talking about compound interest formula. That's why I said some people might like it because it's involving money. You're going to be using the compound interest formula in section 1, but this whole thing is talking about basic exponential functions. We're looking at the difference between growth, decay, how they look, what makes them different, and we're going to be going through that. So why don't you hit pause and basically go through. Juno's opening her first savings account and she's depositing $100. The bank offers 3% annual interest to be calculated at the end of each year. Write a function a of t to model the amount of money in Juno's savings account after t years. Okay, so you're going to have to be writing models. Okay, function models. That means they have an equation in them. That means if it's a model, it has a variable in it. Okay, and recall the compound interest once a year uses n equals 1. The formula above is in the essential ideas. I highlighted it above. So why don't you hit pause, do numbers 1, 2, 3, and 4, okay? In number 4, you're going to have to use dead mouse to find the intersection or guess and check. Okay, so we're back, and like I said before, P is going to be your initial investment. They tell you that represents the principal amount, the amount you originally deposited. R is the rate of interest, always has to be put in as a decimal. N is the number of times compounded per year, and T is always in years. So if I look at this, if I put $100 in, there's my P, okay? So there's my P. This 1 is always there, plus my rate, 3% is 0.03, divided by N. N is 1 because I'm getting interest once a year, raised to the 1 times T. So my model could look like that, or I know 0.03 over 1 is 0.03, and I can put 1 plus 0.03, and I can throw my equation just like that in this instance if I want. Well, the next problem wants you to calculate how much Juno had in his account at the end of 1 year. So that just means you put a 1 in for T, and you can see, hopefully you can see, that he's going to have $103 in his account, which means made $3 interest that year. The next one, how much is in there after 5 years? Well, now I just got to plug a 5 in for T, and I don't know what happened to my decimal place there. So it's going to be $115.93 is how much at the end of 5 years. And then this last one says, at this rate, how many years will it take Juno to double her initial investment of $100? So what you want to do is you want to find when her equation for interest is going to equal twice the amount she put in. So when is it 200? Okay. Well, bottom line, you are unable to solve this algebraically because it takes something called a logarithm. You've heard me talking about those quite a bit, and you don't know anything about those little buggers. So you got two choices. You can guess and check, or you can use dead mouse. I typed it into dead mouse here, and what you're going to do is you're going to type y equals 200, because if you don't put a y on it, it's going to probably type a vertical line, or it's going to type nothing, I don't know. And the other one is basically y equals 100, or the interest account, and you find out the intersection of those two, and you can see it's going to be at 23.45 years when he is going to have $200 in his account. So basically, how long is it going to take her to double her investment if it's taking 23.45 years to double? Remember, you're only getting paid interest once a year, so it's going to take 24 years. Okay? Because it's going to be at the end of the 23rd year before you get interest, and then it's going to be more than double. Okay? So what we're going to be doing here is, what I'd like you to do is I would like you to go through all 6 of these graphs here. And what I want you to do first is label each one. You don't have to cut them out. Label each one of these graphs as either a growth or a decay function. Okay? And then we're going to go complete the tables below, and then we're going to match each table with the graph. Well, it's not that bad. Remember, the first part's easy, identifying growth or decay, because as you read a graph the same way you read a book, from left to right. And if your graph is going up from left to right, it's an, well, with this shape, I should say, it's an exponential growth function. It's a growing function if it's going up. So this first one is definitely a growth function. The second one from left to right is actually coming down. So it's a decay function. The third one is going down. It is a decay function. The fourth one down here, it's not going up nearly as fast as the one above it, but it's growing, so it's a growth. Hey, this other one, that's going up. It's going up at a rate that's kind of, well, I wouldn't say between, but it's going up faster than this one and slower than that one, but it's still growth. And the last one is going down, right? And so it's a decay. Well, next thing I'd like you to do is I'm going to hit pause, and this should only really take you a minute or so, okay? And I want you to fill out these tables of values here. So what they're doing is they're giving us a function, and I'll fix that in a minute. They're giving us a function here, and you need to fill out the type. Well, what is 3 to the negative 1/2 power? Please don't give me a decimal, guys. Give me it as a fraction, a third. What is 3 to the 0? It's 1. What is 3 to the first? It's 3. Fill out the rest of these tables, and then we're going to match each table to which graph it is, and there's a logical way to do this, okay? So why don't you hit pause and finish these out. Okay, so hopefully you remember a little bit here that, like I said, please don't type in 3 raised to the negative 1 power, because, you know, you guys should know what a negative exponent does to a fraction is it takes what the negative exponent is and it moves it to the opposite spot of where it is. So that's why it's a third, okay? It just flips it over. And if it's a whole thing, when I'm looking here at this decay, 0.1 is 1 over 10 to the x. 1.5, I really don't like decimals, I'll be honest. 1.5 is really 3 over 2. So that when I take 3 over 2 to the negative 1 power, if it's over a whole fraction, it just flips the fraction, is all a negative exponent does to a fraction, okay? And now what we're going to do is we're going to be looking up here, we're going to match these to graphs. Now, we said we had 3 growth functions, right? And one grows fastest, and one is growing the slowest. And one is in the middle of those two. Okay, so how do I differentiate? How do I know which one is growing faster? Well, we should have figured that one out last Friday, I think it was, when we were looking at the growing at a penny. If it doubled, your growth rate was 2, as opposed to 50%, your growth rate was 1.5, and the 2 grew faster. So our growth that we're looking at, whatever the exponent is over, whichever the biggest number is the fastest growth. So that first one needs to be A, or I'm sorry, the one with a 10, that's A. The slowest growing one was my slowest or my lowest number of 1.5, and that was D. And then when I looked at E was right in the middle. And also when I'm looking at my decay functions, look at this one. This one decays the fastest because it's the steepest. It comes down the steepest. This is the slowest, okay? and this one's in the middle. Well, if it's decaying, remember, from Algebra 1, if it's decaying, well, now there's something going on with my B value in there. And my steepest decay, the fastest I decay, would be the smallest number that we got there. And 1/10 is the smallest, so that's going to be graph B. Okay? And then which one's the least decaying? Well, that's going to be kind of in the 2/3, okay? Because that's going to be closer. That's bigger. It's a lot bigger. It's the biggest decay. Therefore, it's the slowest decay, which is F. And the one that's in the middle here is C. Okay, so that's all you're doing is you're matching those graphs up. But now what we're going to do is we're going to analyze those graphs. So you might want to look at both of them at the same time, okay? And analyze the exponential growth and decay functions. And what I did was I kind of took the liberty here to say, hey, here is an exponential function in function form. It's a times b raised to the power of x. And I wrote a little note for you there. If you look at all the growth and decay functions you had, the A value is 1 for all of those graphs. And that's kind of important. That's a pretty important thing to identify, but that's keeping them all the same. And when you look at all of those graphs, or you look at all of those tables, what singular, what one point do all 6 of those graphs have in common? And the answer to that question is their y-intercept. Their y-intercept is at 0. Why is their y-intercept, no pun intended, why is their y-intercept at 0? Well, the reason for that is it's because any base to a power is 0. If you come back here and you look, okay, here's my y-intercept. Oh, darn it. Here's my y-intercept right here, and right here. Those are my y-intercepts for all of these, except I have a 0. What the heck do I got going on there? Those all should be 1s. I don't know what I'm thinking. Those need to be 1s. That's a 1, that's a 1. Why is it a 1? Because 0.1 to the power of 0 equals 1. Anything to the exponent of 0 equals 1. Anything. And if you look here, all of these functions, and I gotta take these back off again, all of these functions here, my exponent, my x, so if I put a 0 in there, I am going to be going through the point 0, 1, because anything to the power of 0 is 1, okay? Compare the equations of the 6 functions that we just matched. What differentiates a growth from a decay, okay? Well, what do you notice about the growth? The growth functions all have what in them? Their b factor is bigger than 1, okay? What were they all? We had 1 with 10, 1 with 3, 1 with 1.5. And the bigger that b value got, the faster it grew. How about the decays? Well, our b value was between 0 and 1. Not an absolute value of b. It cannot be, no pun intended, b cannot be negative and still be an exponential function. And we're going to see that. We're going to see that right down here, okay? We'll see that in a minute. But decay is always between 0 to 1. The closer that fraction is to the number 1, okay, the closer it is to 1, the slower it's going to decay. The closer it is to 0, the faster it's going to decay. So it's just kind of backwards of what you usually think, okay? So what we're going to do is, what I really want you to do is, I'm not going to take the time to do this, but you should take the time to do this if you really want to learn this, okay? I want you, with Desmos, explore these 3 different graphs. What do you mean these 3 different graphs? Well, I want you to look at y equals 0 to the x when b is 0. I want you to look at y equals 1 to the x. And I want you to look at y equals any negative number raised to the power of x. And I want you to look at those 3 graphs. Graph them all in the same decimals, so do them each in a different color, okay? And tell me what you see, and explore those graphs, and we'll discuss our findings down here in just a second. Well, if you looked at your y equals 0 raised to the x power, what you should have found is that's a constant function running along the x-axis, but it is only on the x-axis for greater than 0. Well, why? Well, the short version is because. Actually, I lied. But if I add 0 to the negative 1 power, remember what negative exponents do. That's making me look at 1 over 0. And what is 1 over 0? It does not exist. It is undefined. It's rising 1, running none. It's an undefined slope. It does not exist, okay? Well, what if b equaled 1? What did we have? Well, what is 1 raised to any power? It's 1, okay? Again, it was a constant function. The graph was y equals 1. You should have seen a horizontal line going across there. Now the wild one, if b was a negative number, that looks like negative pi, but it's really a negative number, what happened? Well, that sucker was all over the place, wasn't it? It went up, it went down, it went up, it went down. Well, why is that? Well, think about it. If you take a negative number to a positive, you take a negative number to an even exponent, it is now positive. But if you take that same negative number to an odd exponent, it's now negative. So your y values are oscillating from positive to negative, from positive to negative. And that happening, that's not an exponential function. That's an oscillating graph, okay? So it's not going to be there. Well, keep on a trucking here. Write an exponential function of the form y equals b to the x with the given characteristics. I wrote you that note again. Note, a equals 1 for all of these problems. They're not always going to equal 1 after today. They may change, okay? So that's why I keep putting that note in there. Well, if we're going to write an exponential function giving these conditions, if it's increasing, I know it's a growth, right? Which means b has to be greater than 1, doesn't it? It's got to be greater than 1. And if I'm looking at y equals some b times x, and I plug my 6 in for y, and it looks like a b, that's my 6, b, and my x is up here as 1, well, b to what power gives me 6? Well, wouldn't this imply b has to equal 6? And if b equals 6, my function would be y equals 6 to the power of x. Because now, when I plug a 1 in for x, I get a 6 out for y, okay? Well, how about the next one? If it's decreasing from negative infinity to infinity, hey, that means it's a decay function, which means b has to be greater than 0 but less than 1. Can it be negative? No, it cannot. Okay, so we're going to take y equals b to the x, and what we're going to do, we're going to plug in our y, which is 4. We're going to plug in our x on the b, and that's a negative 1. Whoa, I really don't know what's going on here, so now I'm going to say, well, let's look at this as 4 equals 1 over b. Let's cross multiply this like a proportion. This is going to give me, I'm going to say 4b equals 1. So wouldn't that mean b has to equal 1/4? Well, isn't that kind of crafty? So what's my function? Y equals 1/4 raised to the power of x. Well, it worked out really nice because it is a decay, because 1/4 is between 0 and 1. Okay? Now, my end behavior on this last one for part C, your end behavior, as x goes to negative infinity, f of x goes to 0, and as x goes to positive infinity, f of x goes to infinity. Hey, that's pointing you out like this. What is that? That's growth. That's so growth. Okay, so think about it, make a sketch. It's a growth function, so we know b has to be greater than 0. And if our reference point for our y equals b to the x, if our reference point is going to be 6.25 equals b squared, or, excuse me, b, shouldn't have said that, b to the second power, what does b need to be? Fumble. Not really. But we're going to solve this for b. In order to solve for b, we're going to have to square root, which means b equals, oh, that's right, but when we square root, we have a positive and negative root come out. Oh, boy. I wonder if 6.25 is a perfect square. You betcha it is. It's 2.5. But remember, it has to be a growth function, which means b has to be great. Ooh, it can't be negative and still be an exponential function. So b must be positive, which means I can come back here and I can say, let's get rid of this. This is one of those crafty times. If I forget about my negative, it's a positive thing. So there's my b value. So what is my equation? My equation is y equals 2.5 raised to the power of x. And check it out. If I plug a 2 in for x, 2.5 times 2.5, you know what it is? It's 6.25. Okay? Last page we're on here. I took the liberty of just making a growth function and a decay function for you. And what I would like you to do is hit pause. Feel free to look at my graphs as you're filling out this table, and this is going to round us out for the day. So I'm going to fill mine out, you fill yours out, and remember this is going to be for y equals b to the x. Again, our a value is going to be 1, okay? Fill it out. Okay, hopefully you're back, and hopefully you were looking at my graph. So remember, domain. Domain is always talking about x's, okay? And if I look at this, my domain is all real numbers because even as that graph goes straight up, it's still creeping to the right. So for every x value I put in there, it just gets bigger. It's just going to get super big as it goes way out there. And this, the same for my decay functions, okay? As I put a smaller negative number in for x up here, okay, if I flip a fraction with a negative number, if that fraction's less than 1, it's now more than 1, which makes it way high over here. But notice I can put any x I want in there and I will get a y value out. But I won't get any old y value out, will I, if you look at that? Okay, notice your range. Range is always talking about y values only. And notice, this thing never falls below 0. Well, I can tell you the equation of this is y equals 2 to the power of x. And regardless, is there any way to take a positive number to a power? Can you raise a positive number to a power and ever get it to be 0? No. You can get it to be really, really small. That's why the range is all real numbers greater than 0, or you say 0 to infinity, and I do not include that 0 because I will never get at 0. And the same thing over here. This one's y equals 1/2 to the power of x. Can I raise a positive number, 1/2? Can I raise that, number 1, to any exponent? Can I take a positive number times itself as many times as I want? Number 1, it can never be negative. That's why the graph is never below the x-axis here. Nor will it ever get to 0. Okay? It's going to get really, really close to 0. But that brings in this whole understanding of what a horizontal asymptote is. There's a horizontal asymptote at both of these, and your calculators and Desmos don't graph them. We will graph them sooner or later here, and they are imaginary, invisible dashed lines that your graph gets snug as a bug in a rug to, and they are both at y equals 0. Y-intercepts, well, check it out. They're both at 0, 1. And I have some blue boxes there that I'm going to come back to in a second. My end behavior, so as x goes to negative infinity for my growth, so as x goes to negative infinity, my graph is getting snug as a bug in a rug to 0. And that little plus, that just means from the top side down. It's kind of coming down like that, but it's always going to be positive, okay? And as x goes to positive infinity, ooh, y spiking. It's going up fast. It's going to infinity. Well, look at my basic decay. So as x goes to negative infinity, where's my graph going? Oh, it's going to positive infinity. And as my x's are going to positive infinity, my graph is coming down. It's getting snug as a bug in a rug to the number 0 from the top side, or the positive numbers. That's what that little plus means, okay? Intervals of increase and decrease. Well, if I look, I really got to unjunk this thing up. Okay? If I look at my growth function, as I'm coming across, it doesn't look like it's doing much here, but it's slowly creeping, and then all of a sudden it hits a spot, and boom, and it shoots up. Just like as we were doubling our penny, went from 1 penny to 2 pennies to 4 pennies to 8 pennies to 16 pennies, or to 8 pennies to 16 pennies. It grew really slow, and then bang, it shot up really fast. But a growth function is always increasing from negative infinity to infinity, and a decay function from left to right, a decay function is always decreasing because it's coming down. Even the further out I get here, it's just making really small trips closer to the x-axis, okay? And the last thing I want to talk about here quick are these x-intercepts, because if I have y equals some number a times b to the x, okay, and I'm thinking of intercepts, y-intercepts, okay, I only have a y-intercept, and I better clarify that with this. It's a y-intercept. These guys don't have x-intercepts. But if I put a 0, y equals a times b to the 0, any number to the power of 0 is 1, and that's going to be multiplied times a. So if I have an a value, my y-intercept is going to be at 0, comma a, because that is going to go to 0. So that's what I just have written in there yet. If y equals, if I have an a value, my y-intercept will be 0, comma a. That's why I said be careful, okay? All of ours in this problem were always, our a value was 1, but they're going to change on you, all right? Sorry for the length of this. Everybody watches them at 1.5 or 2 speed anyway, so have a good rest of your day. We'll talk to you tomorrow.